Okay, here we have a claim, and we may want to either prove or disprove this claim. So two things I want to mention, specifically the divides symbol. I want to talk about how to convert that algebraically, and then second, how to approach a proof like this in general. So the divide symbol, we can say that m divides n if and only if there exists some integer k such that mk equals n. Now this may not look simpler than this, but a lot of times the longer it is, the more you can actually dig into it in detail. So concise isn't always the easiest to work with, even if it is nice in certain situations. So I'd much rather work with this statement down here in a proof than I would this. Whenever I have a proof involving the divide symbol, I'm going to think about these two different ways to represent that relationship. And if they're putting it like this, I'm going to consider converting it to something like this. So that's the divide symbol in general. Now, there's also the larger idea of how to approach this proof. I would tend to plug in some numbers first of all. So I have three integers. I want a to either divide b or c, and then I want to see if a divides b, c. So maybe I let a be, let's say, 3. B, I want to make sure a divides b, so I'm going to maybe say that's 12. And c, it doesn't really matter. Let's keep it small at 2. So a does divide b, so we meet the if part. Does a divide b, c? Well, 3 does divide 24. So in that case, it works. We found at least one case where it works, certainly not a proof. We maybe try to break it. Let's say that b is 0. So let's use a equals 2, b equals 0. So 2 will divide 0, right? Because 2 times 0 equals 0 by that definition there. And then let's let c. Is there a way we can break this with c? Well, probably not, because no matter what c is, whatever c is, 0 times c is going to be 0, and then a is going to divide that. So again, we have another case that works here. So 2 does divide 0. So we could play around until we start to think, okay, I'm thinking it does work. If we're thinking it doesn't work, that's when we really try to push hard for counter examples. Maybe if we use 0 or a prime, or are we allowed to use negatives? And here it says any integers, so we could use negatives. If we start to feel that it is going to be true, then we want to maybe go through with a proof. So let's try to prove it here. Proof. Let a, b, and c be integers such that a divides b. So because there's nothing special about b or c, if a would divide the c, we would just switch c and b here anyway. We could say it's called without loss of generality. In other words, if we're allowed to have one of these, let's go ahead and just say it's a divides b. So then the question is, will a divide b times c? So since a divides b, there exists an integer k such that ak equals b. So again, I'm using that definition here. That's where I'm pulling it in. So since a divides b, we know this integer, and now I start to think, okay, what's the finish line? How do I know when I'm done? Well, if I have a times some integer equals b times c, then I'm done because I've shown that I met the original statement, and then I was able to show that the then part was true. So how could I do that? Well, if I just want a times some integer equals bc, what if I try to make the right side equal to bc already? multiplying by c, we get, and you do want this to flow like written English. So we would get AKC equals BC. We have to do, whatever we do to the right side, we have to do the left side also. And this is actually really good news. All we had to show was that A times some integer equals BC. Well, since this right here is an integer, by closure of the integers under multiplication, I don't know if I got all the letters in there. KC is an integer, and so A divides BC. And again, it was either one of these were true. If A divides C instead of A divides B, we would use the same exact proof. So it's without loss of generality, this would be true in either case. And so you have your nice proof symbol there, and you are done.